Hi, welcome back to Discovering Patterns in the Microbiome. In this video, we will continue to discuss ordination techniques, specifically the horseshoe effect, sometimes called arch effect, and detrending. Now, we've seen how different distance metrics can do a better or worse job at recovering a gradient in a particular set of microbiome data points. But in all cases, when it does a good job of recovering it, it tends to have this very strong, what we call arch effect, or it's like an arch or a horseshoe shape. So sometimes it's an arch like you see in the chi-square distances here. Sometimes it actually curves back in on itself, which you see in the Bray-Curtis distances. And most people think of the arch as being an artifact of the ordination technique. So you'll see this on Mike Palmer's page. Arch effect is a distortion or artifact in the ordination technique. But if you and the way people think of it is that something about the ordination is making the ends of the gradient kind of curve back toward each other. What you really want to see is that the ends are far apart and as far apart from each other as any of the samples are, and the middle is sort of in between the two, which would be this detrended version here. But if you compare the actual distances between samples in the raw principal coordinates analysis with the arch effect to the true distances between samples, and here this is using Bray-Curtis, you see that there's a pretty good correlation. So that's what's shown in the lower left. You see the the expected distances, that's the full distance matrix on the x-axis, the principal coordinates distances, so that's literally the Euclidean distance on the piece of paper or the slide. On the y-axis, there's a nice scatter plot there, nice y equals x correlation. If you compare the distances in this detrended version, and we'll talk about how we get that version later. So this is, again, literally like taking a ruler and measuring how far apart the points are from each other on the slide, to the actual ecological distances between samples using Bray-Curtis, then you get this scatter plot. So which one is more accurate? Turns out the principal coordinates analysis is a more accurate representation of the true distances in the distance matrix, and detrended scores are actually less accurate. So it's not always something, the arch effect is not necessarily an artifact of the ordination. It's actually something that's present in the original distance matrix. And this is sort of an open question. Could there be a better distance metric that would remove the arch effect? In other words, it wouldn't show that that the ends of the gradient are about as far apart from each other as they are from the middle of the gradient, and it would show that they're as far apart as possible. But that's not actually what we see using the common distance metrics. Nonetheless, there have been attempts to remove that arch effect, and there's a bit of literature on this. The way that people have done this in the past is usually through detrended correspondence analysis. So we haven't gone into depth about correspondence analysis too much yet. We'll do that when we're discussing constrained ordination. But the same thing would apply to principal coordinates analysis. So basically you do the ordination, you get an arch, and which could go down or up, because remember the sign of the axes is totally arbitrary. Then the way this works is it just slices up the x-axis into bins, say 10 bins, and shifts those bins up or down to have the same mean. And then those are the new detrended coordinates. Turns out this is really not a good idea because, well, the size of the bins is going to matter, and it's hard to know what size to make them. Here's what happens if you run the detrended correspondence analysis in the vegan package. In R, on the same Bray-Curtis arch. So we're using that technique where it chops it up, and what happens is we get this weird effect where like the whole beginning of the gradient gets shifted down and the whole end of the gradient gets shifted down together. Even though what you really want is to be following the gradient, more steeply at the beginning, and then leveling off and then curving back up with it. So this is kind of like a piecewise linear approach, and often has issues. It turns out that you can actually fit a curve to this and detrend it. It's not really any less hacky than the detrended correspondence analysis solution, but from my experience, it gives better results. So I call this iterative quadratic projection. I'm going to explain it to you in a minute. It gives you results that look like this center figure rather than results that look like the figure on the right from detrended correspondence analysis. So iterative quadratic projection, very simple approach. It takes the first two axes of PCOA, where you have this arch effect, tries to fit a quadratic function to the data. Then it projects the points to their nearest position on the curve, and then just kind of unfolds them. If there's any curvature left, it fits another quadratic, projects the points onto the curve and unfolds them again, and it repeats until there's no change. So here's an example of applying this to the global gut study. This is a study where we have a very strong age gradient, just looking at individuals in the USA here. And so the samples on one end are infants and on the other end are older adults. The original data are shown in this top left panel where you see the strong arch effect. So the age gradient is clearly the strongest driver of variation. That's what you see along the x-axis, but it's also interacting with the second principal axis of variation. So you can see in the first figure, there's a quadratic curve. The points are being projected onto the curve perpendicularly, and then the curve is being unfolded, and you get the next figure in the first row. Then we go down to the next step. We fit another curve, project the points, straighten it out, and we do it 2 more times. And then what you get at the end is this final set of projected coordinates, where now age is almost perfectly correlated with axis 1, and most of the correlation of age with axis 2 has been removed. It's important to note that the detrending approach, whether it's this or the detrended correspondence analysis, doesn't know about age, or in the case of the Guerrero-Negro data, doesn't know about depth. So it's a way of demonstrating that the principal variation in the data is driven by a particular geochemical or other experimental gradient. And then you can have a nice pretty picture where you don't have that weird arch in it. Okay, that's nice. You might also start to ask, is the residual variation that's left over after you've regressed out that arch related to some other factor in your data? Now I want to do a little code demo of detrending in QIIME. So we'll go back to the course code browser, back to the ordination page, and right to the point where we had finished doing the biplots in QIIME. You can do detrending in QIIME. The command is dtrend.py. The current version of QIIME has an issue where you have to remove some extra lines at the top and bottom of the principal coordinates file to get it to run to get the detrending to run. So here's a little command you can use to do that. It's basically stripping off the first 9 lines and the last 4 lines in the file, and then saving it in a new file. So here's the original file. then here's the file that we're saving that has those lines stripped off. So once you've done that, you can run dtrend.py on the new file. There's a particular flag for that you can set for suppressing pre-rotation. So what happens is before it starts fitting that quadratic curve, by default, the command will try also rotating to get the best correlation of the first axis with whatever gradient you pass to it. And I recommend actually not setting this if you have a nice U shape or upside down U shape, only using the pre-rotation if it's kind of a crooked, like diagonal U shape. So so here's how you run this. Quite straightforward. You pass in the modified principal coordinates file. You have to give it a mapping file or a metadata table and the name with this -c, the name of a column that has the continuous values you think are related to the primary gradient in the data. Then you tell it what output folder you want to use. So we can run this command. This is to be run on the command line, not in R. So now it just ran, and we can print out the contents of this summary.txt file, which are shown right here. So it provides the correlation of whatever gradient you passed in. Here it was the end depth of each sample with PC1. And it tells you the correlation before detrending and after detrending. So here we see that PC1 was already very highly correlated with depth. It happens to be inversely correlated, but remember, we don't care about that because the axis sign doesn't matter. After detrending, we have an even stronger correlation of 0.98. So the correlation of depth with PC1 increased. Then it gives you the correlation of PC2 with the depth, and what you see. So what you see is that it says it's doing piecewise correlation. So it breaks up, if you have this arch, it breaks it up into two halves and fits a line to this half, or it does a correlation on this half and another correlation on that half, and takes the average of their absolute values. So here we get 0.65 before detrending, and it's now gone down to 0.42 after detrending. And then finally, it gives you the Spearman correlation of the detrended distances with the original distances. And so you could report, for example, if you want to use this in a paper, you could report this correlation score after detrending and this p-value. Then there's a PDF in the output table that shows you the gradient, the plot colored by the gradient before the detrending and after the detrending, and if you want, you can show both of them, or you can just show the detrended values. In summary, detrending doesn't really have a strong statistical foundation. It's just trying to get rid of this weird, ugly arch or horseshoe effect. There's even some controversy still about what's causing the arch effect. But you can use detrending if you want as a convenient way to visualize the primary gradient in your data. You can use it to test whether your ordination recovered the primary gradient in the first axis of variation. So you can actually do a correlation and get a p-value for that. And the p-value is likely to be better after detrending than it would be without detrending. It's important when you're reporting that to remember that the detrending didn't know about whatever gradient there was. So if you had this age gradient or depth gradient, the detrending is totally unsupervised. So if it happens to recover that gradient really well, then that means that it's probably a real signal. You can use QIIME for detrending, although in QIIME you have to remove the first 9 lines and the last 4 lines of the PCOA file if you're using version 1.9. I gave you a little example of that in the code browser. And I recommend using QIIME for detrending because it has this slightly more effective way of actually removing the curvature than using simple piecewise detrending that you would find in the vegan package in R. And that's all for this video. In the next video, we will be discussing ways of doing constrained ordination to understand how the ordination is related to multiple axes of variation in the data.